What's up? I bet you thought I was going to say what's going on, Algebros. Well, now that I said it, what's going on, Algebros? It's Mr. C here. And in this video, we're going to solve another inequality. This time, though, it's not a polynomial inequality, but rather it's it's an inequality involving a rational expression, hence a rational inequality. First thing that we're going to want to do is make the right-hand side 0. And the easiest way to do that is to minus the 1 over to the left-hand side. So we're going to have x plus 13 over x minus 18 minus 1 being greater than or equal to 0. So that accomplishes that task. The next task, though, is to make sure that the expression on the left-hand side is just a single solid fraction. So unfortunately, what that means is that we're going to have to do some work with fractions, in particular subtracting two fractions. Because really, you can think of the minus 1 as minus 1 over 1. And so that gives us a clue as to what to do next. We would need a common denominator, and the common denominator would be the expression x minus 18. So for that reason, I'm going to multiply the bottom of the 1 over 1 by x minus 18, as well as the top by x minus 18. So we're looking at x plus 13 over x minus 18 minus, and I'm going to keep the numerator in parentheses, you'll see why in just a second, x minus 18 over x minus 18. And that's still greater than or equal to 0. Now that we have the common denominator, we can go ahead and subtract the two fractions. We'll have x plus 13 minus quantity x minus 18 all over one copy of x minus 18. And this is why I chose to leave the numerator of the second fraction in parentheses, because you're going to have to distribute the negative to each of the two terms. So that's x plus 13 minus x plus 18 all over x minus 18. So it looks like the top will simplify. Looks like the x's cancel out. And 13 plus 18 is going to give us 31. So the single solid fraction is 31 all over x minus 18. And now that we have the left-hand side as a single fraction, what you'd want to do next is factor the top and bottom if possible. In this case, it's not possible, so this is what I'm going to define as my function f of x. Now, some of the process of solving polynomial inequalities will resonate with the process of solving rational inequalities as well. But there's an additional thing that we do. We not only try to find the zeros of the rational function, but we also want to find the vertical asymptotes. So in this next part, we want to figure out the zeros and also the vertical asymptotes. And the zeros are found by taking the numerator of the rational function and setting it equal to 0. That would amount to 31 equals 0, which that's obviously a false statement. So this rational function actually has no zeros, or I'll put none. However, it does have a vertical asymptote, and how we can sniff that out is take the denominator, set it equal to 0. That's x minus 18 equals 0, and we get x equals 18. So there is a vertical asymptote, and that happens with the x value of 18. So all zeros and vertical asymptotes, if you have them, will be plotted on the number line. In this case, we just have a vertical asymptote, so I'll put 18 there. And we're going to test the two different regions of the x-axis that are created by putting 18 on the number line. To the left of 18, we'll pick a number that's less than it, maybe 0. If we were to plug 0 into the function, we'd have 31 over negative 18. And that is a negative number. So what this means about this result is that any value of x that's less than 18 will make the rational function f of x negative. Let's pick a number larger than 18, maybe 20. So if we plug 20 into the rational function, we get 31 over 2, which of course that's a positive fraction. So any value of x that's larger than 18 will make the rational function f of x positive. Now which of these two sections of the number line do we want? Well, let's go back up to this pairing of the inequality symbol and 0. If we want something to be greater than or equal to 0, we basically want something to be positive. So we want the positive section of this number line, and the positive section of this number line goes from 18 all the way to positive infinity. So the interval notation would be 18 comma infinity, by default, parenthesis on the infinity. Now, be careful. I know there's a bar underneath the inequality symbol, so that would maybe motivate you to put a bracket around 18, but even though there's a bar, I'm still going to use a parenthesis around 18, and the reason for that is because 18, you got to keep in mind, is a vertical asymptote. So regardless, even though 18 helps us a lot in determining when the function is positive or negative, it's technically not part of the domain of this function, so we couldn't use it as a legitimate x value that could be plugged in. So just kind of keep that in mind. Vertical asymptotes always trump the bar underneath the inequality symbol. All right, so that's our solution, parentheses 18 comma infinity. We'll write that in the space here, and that's a wrap. If you have any questions, let me know. Otherwise, thanks again for watching.